This video is going to look at Voronoi diagrams. A Voronoi diagram is like a map with borders drawn between points in it, indicating the areas that are closest to each point. So in a Voronoi diagram, some terminology that you'll see. Our initial points are called sites. So in these examples below, that's the A, B, C, D. The regions containing the sites, so for example, this section here is called a cell. The boundary lines of cells are called edges, so the blue lines here that I'm just going over in purple on one of them, they are edges. The edges lie along the perpendicular bisectors. So for example, this line here that I've just circled, that is the perpendicular bisector between points C and D. On the second one, that's the perpendicular bisector there between B and C. And say this one here on the final diagram is a perpendicular bisector between A and B. The points where the edges meet, so I'll just put purple dots on the ones in these diagrams, they are called vertices, or if you're only looking at one, a vertex. First example, the following graph shows 5 sites, and they're the coordinates of the sites. The dashed lines show 3 of the perpendicular bisectors, which form edges of the cell containing site E. So it's not all the perpendicular bisectors, just 3 of them. Find the equation of the line which would form the final edge of the cell containing E. Looking at this diagram, you can see we don't have the perpendicular bisector between E and C. We have the perpendicular bisector between E and D, E and A, and E and B. We need to find the one between E and C. So first of all, to find a perpendicular bisector, we need to find the midpoint. So you add the x-coordinates of both points, so it'll be 3 plus 4, and divide that by 2 to find the x-coordinate of the midpoint, and then add the y's of the 2 points, so we're looking at C and E. So it'll be 2 plus 5 divided by 2. And that will give us our midpoint of 3.5 and 3.5. Once we've found the midpoint, we then need to find the gradient of the line EC, so then we can find the perpendicular gradient. So the gradient of EC, y2 minus y1 over x2 minus x1, which will give us 3. And therefore our perpendicular gradient is a negative reciprocal, so it'd be negative 1/3. And now we can work out our equation of the perpendicular bisector. And we do that using our midpoint and our perpendicular gradient. So I always like to use this form of my equation of a line. So we'll have y minus the y coordinate of the midpoint, so 3.5, equals the gradient, negative 1/3, multiplied by x minus the x-coordinate of the midpoint, which is 3.5. Now that's an appropriate equation of a line, especially for the IB. You can rearrange it so it's y equals mx plus c, and if you did that, you would get y equals negative 1/3 x plus 14 on 3. And that's the equation of our perpendicular bisector. Now next we want to add this line to the sketch of the diagram and shade the cell containing E. So here is a diagram with the perpendicular bisector added. Just draw an arrow to that line, this one here, and in blue is the cell containing E. So it's all the perpendicular edges around that point. And in part C, what can you deduce about the point 3,0 by the fact it is in cell containing E? So 3,0 is here. Just put a red dot. What that tells us is that anything within that shaded area is closest to the point E. What we can say from that is that E is the closest site to point 3,0. If we were to complete this Voronoi diagram, it doesn't ask us to do that, but if we were, that is what it would look like when we add all the other perpendicular bisectors and then work out which edges we are to use. Now you could be asked to add a site to an existing Voronoi diagram. There is an algorithm for this, which I have outlined here. I'm not going to talk through it, but it is there for you to have a read of, so you can understand how to add an existing point. Now we're going to do that in example 2. So the diagram below shows in solid green lines a Voronoi diagram for the sites of A, B, C, D and E. We add an additional site F, and the perpendicular bisectors of the line segments connecting F to the other relevant sites are shown as dashed lines. So they've already worked out the perpendicular bisectors of F and all the other points and drawn those in for you. On a sketch, show the new Voronoi diagram for sites A, B, C, D, E and F. So when you add a site, you need to work out perpendicular bisectors for each of those sites, which we've done there in the dotted lines. There's no point in doing one. You'll see here there isn't a perpendicular bisector for F and B, and that's because C is between those 2 points, which means we actually need the perpendicular bisector of F and C. So F is in the cell of site C. So you see here it is in the original cell of C. We're going to follow a pattern. So I'm going to go, well, these two, there's going to have to be a perpendicular bisector. I'm going to go in this direction. I'm now at this point here, which is on the line of the perpendicular bisector of A and F. So we're going to have to go down there. Then we're at a point where we're going to be between A and D, and then between F and E. So that is the shape that separates F from all the other points. But now we need to fill in the rest of the diagram. If we look between A and D here, the perpendicular bisector between A and D, so we'll have that one joined there. And what we'll find is that D and E, we're going to have to carry that one on there. Between C and E would be this one. Between B and C would be that one. And then we can just fill in the rest of the lines that are left. And then we need to remove all the perpendicular bisectors to get the new Voronoi diagram. And so our new Voronoi diagram will look like this. We have nearest neighbour interpolation. Given the values of a function at the sites of a Voronoi diagram, the value of the function at any other point is estimated to be the same as the value at the closest site. That means that the estimates for all the points in one cell will be equal. Example just to show this, the function f has known values at the following sites. So at site A, the value of the function is 16, B is 15, C is 9, D is 8, E is 6, and so on. Used nearest neighbour interpolation to estimate the value of the function at the point 6, 3. So what we need to do here is we need to find out where 6, 3 is on the diagram. So 6, 3 would be here, which is in the cell of G. Now, because it's in the cell of G, it just takes the value of the function at G. So now we go to our table, we look for G, and the value of G is 20, therefore the estimate of the value of the function at 0.63 will also be 20. Then the final thing with Voronoi diagrams is the toxic waste dump problem. And it's another common application is to find the point which is as far as possible from any of the sites. To solve the toxic waste dump problem, for each vertex, calculate its distance from the sites in neighbouring cells. Select the vertex that gives the greatest distance. So last example, an island is modelled by the polygon ABCD. Towns are located at points A, B, C, D, E and F. A toxic waste dump must be located somewhere on the island, but the mayor wants it to be as far from any town as possible. Find the coordinates of the required location. What we want to do here is we want to look at the vertices within the area. So the island is the shaded section, so we have two vertices in there, these two circle points here. So our vertices are at 1, 8 and 16, 8. So these are the two possible sites. Once we've located the vertexes, we then need to find the distance of each vertex to one of the neighbouring sites. Now these vertices, we have to remember, will be equal distance to each of the sites because of the perpendicular bisectors. So therefore we actually need to check one length for each vertex to work out which is the furthest away. So I'm going to do the first vertex to point A and the second vertex to point B. see which distance is the furthest, and that will tell us where this toxic waste dump needs to be placed. So we went from 1, 8 to A, which is at 0, 0, and remember our distance formula. So this will be the square root of 1 minus 0 all squared plus 8 minus 0 all squared, which will give us an answer of the square root of 65. And then we want to do from 16, 8, and we'll do it to B, which is at 20, 0. So we'll do 20 minus 16 all squared plus 0 minus 8 all squared, and that gives us a solution of the square root of 80. Now the biggest distance there will be the square root of 80, therefore the required location for the toxic waste dump would be at 16, 8. And that's Voronoi diagrams.